let us start. We're going to learn about satellites in orbit. We'll learn how to find the speed of satellites in circular orbit around our Earth. We'll learn how to find the period of orbit, that is the time for one revolution. We'll talk about the orbits of spy satellites and the orbits of geosynchronous satellites. And then we're going to show some simulation on the screen so you can see Kepler's 3 laws of planetary motion kind of demonstrated for you. Kepler's 3 laws of planetary motion. And then we're going to, what else? Oh, we're going to talk about Isaac Newton, how he was able to convince people that you could put things in orbit, that it was possible to make earthly objects into heavenly objects. And then finally we'll talk about why banked curves work. So it's a lot of learning today. A lot of learning. Satellites in circular orbit. Alrighty. Well, first of all, if you've got some planet and you've got some satellite orbiting the planet, and we're going to make them circular orbits, okay? This satellite's moving in a circle, so something is responsible for making it move in a circle. Tell me, what is providing the centripetal force for the satellite to move in a circle? Yeah, gravity. So when we do F equals ma, the only force acting on this satellite is gravitational force. And so I end up, for the gravitational force, using Newton's law of universal gravitation, where big M is the mass of the planet, little m will be the mass of the satellite. And on the right side, because I'm moving in a circle, what am I going to put in for A? V squared over R. Beautiful, thank you. V squared over R. Great. Does it matter what mass my satellite is? Is that going to affect its speed or where it's positioned?
No.
Heck no. Mass does not matter, not the mass of the satellite anyway. Good. And so really, this formula will get you there. Almost any question they ask you about satellites in orbit, you can just always start with this formula. If they give you mass and velocity and ask for radius, you can solve for r. If they give you mass and radius and ask for velocity, you can solve for v. It's all there for you. All you have to remember is that what's providing the centripetal force is gravity. Now, our textbook likes to solve for v, so our textbook goes v equals the square root of g times the mass of the planet over the radius of curvature, over the radius of the orbit. You know, that's what our textbook does, but you don't need to memorize this. This is good enough, and then work with it however you want. So let me give you a problem where you get to work with this sort of thing. Spy satellites, they want to be as close to the Earth as possible because they want to spy on you, right? So they need to be close so they can spy on you, okay? What's another type of satellite that you want to be pretty close to the Earth? Yes, cell phone satellites, that's good if you're going to be using those satellites for your cell phones. What else? What's that? Yeah, GPS, sure. You'd like them to be pretty close. You know, the closer they are, the more accurate they're going to be. You know, I sometimes wonder about the Apple Find My iPhone, you know, because, yeah, I say, where's the iPhone? And it'll give me like plus or minus 2 blocks. I go, well, how close is that satellite? But yeah, or maybe weather satellites. Okay, so let's go ahead and get a satellite that's close. Here's example number 1, okay? I'm going to have G equaling 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, the universal gravitational constant. The mass of the Earth is 5.98 times 10 to the 24th kilograms, according to my textbook. The radius of the Earth is 6.38 times 10 to the 6th meters, according to my book. So this radius from here to here is 6 point, we'll just call that the radius of the Earth. radius of the Earth. And then I'm going to have a close orbit, which means the satellite's going to be just barely above the Earth's atmosphere. We'll say the satellite is 100 kilometers or 100,000 meters above Earth's surface. That way it's safely above the atmosphere. I'd like you to find the speed. So go ahead and do the punchy and let's see what happens for you. And I just want to show you visually, many of you have already started, but visually, this distance is 100,000 meters. The distance of the satellite above Earth's surface. I'm hoping that everybody, for their radius, is adding the radius of the Earth to the distance that the satellite is above Earth's surface. If you didn't add those two together, then you're going to get a bad answer. So is anyone getting an answer? What'd you get? What'd you get, Frida?
I forgot to add them.
What'd you get, Earl?
I don't have a calculator.
Huh?
What?
9.5.
9.5?
Yeah.
No, I'm so sorry, that's wrong. What'd you get, Justin?
7,792.9.
Wow.
Yeah,
I
about
was really-
7,800. Okay? About 7,800. Actually, if you use all of the sig figs, it should be like 7,846, is it? Is that what you got? 7,846? Okay. How many people got 7,846? Okay, well, about a quarter of the class. So the rest of you, you're going to have to get better at punchy on the calculator. And if you're having trouble getting right answers, please see me after school because there's something systematically wrong that you're doing. And that's okay.
Or they have a demon-possessed calculator. Or they have a demon-possessed calculator.
Yeah, or it could be, you're right, it could be the devil himself. Okay, well, now that we've got your speed, and that's pretty darn fast. If you want to go around in a circle, you're going to have to be going pretty darn fast to go around in that circle. So that's how fast those spy satellites go. Okay, so the next question I want to ask is, how much time does it take the spy satellite to do one orbit? That is, what is the period? What is the period
Oh, shut up, white boy.
of orbit? The way, that is another way of putting it is, how much time does it take to complete one revolution? Time for one, I don't know, revolution, I guess, or one orbit. Okay? Here's the way you're going to do this sort of problem. You're going to start with x equals vt. Okay? The distance you travel is one revolution, which is 2 pi r, correct? So it'll be 2 pi r. and that's going to equal your velocity times. And we give a special variable for the time of one revolution, or the time of one period. We call it capital T. That's the period. I don't know if you remember that from pre-calculus, those of you who've had pre-calculus, but period is always called capital T. So I got capital T. So now I'm going to have 2 times pi times 6 point. Do you mind if I know that 6.38 times 10 to the 6th, this is 6.38 million. 6.38 million plus 100,000 gets me 6.48 million. Are you guys okay with that? Can I just put 6.48 million for my R? And this is 78.46 meters per second times a period. And so I end up with a period of approximately, if my memory serves, like 86, well, it ends up being like 5,000 something seconds. I guess I will write that down. Just 1 second. Where did I put my calculator? Aha.
You forgot this one.
So I got, oops. Oh, I don't even have it on here. Oh, 78.46, yeah. Oh, well, 2 times 6.48 times 10 to the 6th. Divided by 78.46. So I get to about 5,189 seconds, which when I divide by 60, gets me about 86.5 minutes. So that's what you got. Yes?
Couldn't you also use dimensional analysis to figure it out, so that you just cancel out the units by using the rate, multiplying it by 1?
Absolutely. So what Chris is advocating is going, hey, why not just take 7846 meters per second and then say, okay, I've got 1 revolution in, 2 pi r. Okay, is that what you did?
Yeah.
Okay, and then you end up with revolutions per second, and then what did you do?
So then when you just convert it seconds into minutes, and then that's it.
Okay, but the point I want to make is, right now, I'm going to get quote, wait, I'm sorry, wait a second. Wait, okay, there you go. I'm going to get 1.927 times 10 to the negative 4 revolutions per second. That's what I'm getting. When I do this, I get 1.927 times 10 to the negative 4th revolutions per second. So now what should I do?
So then, when you just need to multiply the 60 seconds of time to get per minute.
Well, okay, I could do that, but before I do that, what should I do? Yeah.
The quick question, isn't it supposed to be 6.38 times 10 to the 6?
Well, but I have to add the 100,000 to it.
Oh, yeah.
But I want you to see that if it's 1.927 times 10 to the negative 4th revolutions per second, but I want the period, which is the time for 1 revolution. So the point I'm trying to make is, what you need to do is to get the reciprocal. This is the same as 1 second for 1.927 times 10 to the negative 4th revolutions, which is the same as 5,000, where is that? 5,189 seconds per revolution. Then you would divide by 60. But I just want to let you guys see, you could use unit analysis. And even if you get something that's not entirely right, you can still use your cleverness to figure it out. I mean, if I'm getting this many revolutions per second, then the reciprocal is going to be that many seconds per revolution, and then I get my right answer. So I just want to say that Chris can do it his way, and it's fine. You know,
Good job, Chris.
you don't have to do it my way. Whatever way gets you a right answer. But I want you to see how quickly these spy satellites go around the Earth. So, for example, suppose you've got a spy satellite going over Afghanistan, and it's looking at what may be a terror, base, a terror training camp in Afghanistan. Well, pretty darn soon, what's that satellite going to do? Yeah, pass. Oh, I should probably be on the camera. Pretty soon, that satellite's going to pass out of range, right? You got eyes on this training camp trying to decide if you to blow them up, and then the satellite goes out of range, and it's not going to be back for another 90 minutes. So what are you hoping that there is? This satellite's just gone out of range.
Oh, another one.
Yeah, thank you, another one, right? So how many spy satellites do you think we have up there?
Like a lot.
Are you thinking lots? Yeah, do we know how much? I don't know, it's probably top secret. You know? But we got lots, because we want to have spy satellites looking at everything all the time, right? I assume. I don't know, you know? Okay, well anyway, there's another thing I want to talk about, and that's geosynchronous orbit. Okay. Someone tell me, what is geosynchronous orbit? What does it mean for you to have geosynchronous orbit?
Write that down.
Same orbit as the Earth, right? Geosynchronous. But tell me more. Like here,
It's synchronized
if this is the Earth, and here I gotta pay more attention to the camera. So if this is the Earth and this is the satellite, what does it mean for the satellite to be in geosynchronous orbit? Okay, are you guys okay with that? That as the Earth turns, the satellite turns with it, right? So what would be the period of orbit of a satellite in geosynchronous orbit?
1 day.
What's that? Yeah, 1 day, right? A geosynchronous orbit means the period of orbit is 1 day. So that if you've got a satellite that's directly above Rancho Cucamonga, then at all times that satellite is above Rancho Cucamonga. Tell me, this is something many of you have these dishes on your roofs. What kind of system would have geosynchronous orbit satellites? What's that? What's that? John Carlo? Sure, a satellite television, right? Because is the satellite on your roof, is that satellite moving with the satellite in the sky? No, the satellite on your roof is just stationary, right? Stationary, trusting that the satellite is going to be at the same place at all times, right? Because that satellite, your DirecTV satellite, is in geosynchronous orbit. You see what I mean? And so let's talk about geosynchronous orbit. Let's see how we get it. Geosynchronous orbit. Orbit of period 1 day. Okay. Here's the thing. X equals VT. And so I need 2 pi r to equal V times the period, which means V is going to equal 2 pi r over the period. But we've got another expression for V. Just 1 second. The expression that the book uses, which is the square root of G times M over R. So now I can solve in terms of R and T, in terms of the radius and the period. That is, I get 2 pi r to the 3/2 power over the square root of GM equals T. Or if I square both sides of the equation, I get 4 pi r to the 3rd power over GM equals T squared. Well, this is an example of an incredibly important law that a guy named Johannes Kepler discovered. This is called the 3rd law of planetary motion. And it's actually Kepler's 3rd law. Kepler. How do you spell Kepler? Is it Kepler? Kepler. Is it A-R?
No, that's right.
Is it Kepler? All right. Kepler's third law of planetary motion. Now, his third law of planetary motion really just says this, that the cube of the radius is proportional, not equal to. The cube of the radius is proportional to the square of the period. Here's what happened with Johannes Kepler. There was this guy named Tycho Brahe, and these are all people in the 14 and 1500s before Isaac Newton comes along. So this guy named Tycho Brahe decides he's going to make careful, meticulous measurements of everything in the heavens for his entire life. So this dude spends his entire life making all these incredibly accurate, careful measurements of all the stars, the motion of all the planets, the motions of the moon, the motions of everything he can during his entire life. So he ends up building up volumes and volumes of data of everything he's measured. And then this guy has a student, Johannes Kepler, and Kepler works with all of that data that Tycho Brahe found. And one of the things Kepler discovers is whenever he sees the radius and period of orbit of things, the square of the period is always proportional to the cube of the radius. You know? He always finds that if the period was 4, the radius is 8, or the period's 9, the radius is 27. Only, a proportionality to that effect. The period's 16, the radius is 64. And he finds that true repeatedly. And so he comes up with his third law of planetary motion. Well, then along comes Isaac Newton, and Isaac Newton uses this. Essentially, it's almost as if Isaac Newton started here and ended up, started here to there, all the way to this, force equals Gmm over r squared. Because that's what I did. I essentially started with this and ended up with Kepler's third law of planetary motion. But what Isaac Newton did was he actually started with this and ended up with this. And so this is another example of Newton saying, I wasn't a genius, I just stood on the shoulders of giants. Because without Tycho Brahe, you don't get this, and without this, you don't get that, But anyway, going back to this, okay, I just want to show you that when we plug in all the numbers with the Earth and 1 day and the Earth's radius and g and the mass of the Earth, you end up with a radius of curvature. And I'm not going to go through the awful details, I'm just going to write down the number. You get approximately 4.2 times 10 to the 7th meters. Which means if I multiply by 1 Earth radius for every 6.3 times 10 to the 6th meters, that radius ends up being approximately 6.6 Earth radii away from the center of the Earth. So it turns out, if I can erase this, if this is the Earth, and this is 1 Earth radius from there to there, and you got your SPY satellite that's right here with its period of approximately 90 minutes, then your DirecTV satellite is going to be 6.6 Earth radii away from the center. So there's 1, 2, 3, 4, 5, 6, 0.6. So here's going to be your DirecTV satellite. And I got to tell you, I really didn't realize that when they fire a DirecTV satellite up in the sky, that it was so darn far away from the Earth. I always picture satellites being close to Earth, but no, your geosynchronous orbit satellites are 6.6 Earth radii away from the center of the Earth. Does anyone know where the moon is in all of this? Would you say the moon is far away or the moon is kind of close? Yeah, far away. It's hard to send things to the moon. The moon ends up being 60 Earth radii away. That's the moon. So imagine this distance and then multiplied by about 10. So the moon, if this is where the DirecTV satellite is, and the moon is, well, either into the hall or maybe into Mr. Cabrera's classroom, So the moon's still pretty far away. The moon, in no way is the gravity of the moon significant compared to the gravity of the Earth. The moon is a lot smaller than the Earth, and the moon is really, really far away. So we don't have to really take the moon into account as far as I know. All right. Well, let me see. That's that. So any questions or comments about geosynchronous orbit or spy satellites or DirecTV satellites or anything like that? Does anyone know about, like a student asked me earlier today, is there some agency that coordinates all these satellites so people don't put satellites up there and they bang into other satellites? Does anyone know, is there something like that? Is there, Leilani? Who's in charge of that?
NASA takes care of some of them to make sure that they don't crash. Others deal with the actual orbit path, so that way they can see where the orbit path is, and if they put it in the same distance away, then they make sure that it's a certain distance behind another orbit.
Wow.
Orbiting satellite.
So this is NASA. So we kind of cooperate, even though we're enemies with Russia, we cooperate with Russia on this sort of issue.
Yeah.
Sort of thing.
Well, NASA takes care of their own, and they communicate with others to make sure that ours don't crash into theirs.
Right, there has to be transparency. But so then spy satellites, I guess they're secret just for what they do. Like, we're setting up a satellite, and they go, what's it going to do? Oh, we can't tell you that. but it's a satellite. All right. Okay, great. Well, hey, here's the next thing we need to do. The orbital simulator. I'm going to demonstrate Kepler's 3 laws of motion with this orbital simulator. Yes, I agree.
Are you cold?
You look cold.
Shut up.
Okay. You guys see it okay? Here it comes. Boop. This guy's in circular orbit. Right? Does it look like a circle to you guys?
Yes.
Okay, close enough. Okay, that's a circular orbit. That's because he's going the exact perfect speed to be in circular orbit. I want to remind you again, this kind of handy thing, V equals the square root of G times, in this case, the mass of the Earth over the radius of the orbit. This is going to be true for circular motion. Tell me, what if he goes slower? Here, I'm going to make him go slower. You see that green arrow? That's the velocity vector. I'm going to slow him down. What's going to happen now? What is his orbit going to look like? He's going too slow for circular orbit.
Elliptical.
Well, let's find out. Someone said elliptical. Yeah, you okay? That is elliptical orbit. If you're in orbit, but it's not circular, then it's elliptical. And in fact, look at the point occupied by the center of mass of the planet. This is a moon orbiting a planet. So what special point does the center of mass of the planet seem to occupy? What special point of the ellipse? What's that? Have you guys never learned about this in your Algebra 2 teacher? Ever hear of the focus of an ellipse?
Nope.
No, actually.
Oh, bummer. Well, anyway, an ellipse has two foci, and that planet is occupying one of the foci of the ellipse. It's a shame you guys don't learn that anymore, but that's okay. So that's Kepler's first law of planetary motion. His first law of planetary motion is that orbits are elliptical, and the planet that you're orbiting, or the star that you're orbiting, occupies one of the foci of the ellipse. His first law of planetary motion. Also, I want you to notice something else about this orbit. What do you notice about the speed of the moon when it's close to the planet versus the speed of the moon when it's far from the planet?
It's
Good. Faster when it's closer, slower when it's far. In fact, this effect is really magnified with comets, you know, like Halley's Comet that takes 80-something years to get to us, where when this comet is in our solar system and going around our sun, that comet will be going tens of thousands of miles, like tens of thousands of miles a second or something, miles an hour, I forget, but like really, really fast, okay? Whereas when that comet gets as far from the sun as it can go, you could walk beside the comet. It's going that slow. So you get just tremendous variations in speed. But Kepler's second law of motion, he made this observation. If this is your elliptical orbit, he found that in the time it takes a moon, let's say, to go from there to there, and it takes the same amount of time to go, let's say, from there to there, they sweep out, these orbits sweep out the same area. So this area would be equal to this area if the time from here to here is the same as the time from there to there. So in orbits, the same time sweep out the same areas. That's the second law of planetary motion. And then the third law of planetary motion is essentially right here, that the cube of the radius equals the square of the period. Yeah, so that's Kepler's laws of planetary motion. Here, let me show you something else. What if I go even slower? What shape am I going to get? Oh, you get an explosion. Let's see if that happens again. Maybe it'll be different this time. Explosion again. Okay. Here. Try one more. So what happens? Wait a second. What happens if I send them by? Stop that. What happens if I send them by, but I'm going too fast?
Yeah, it'll leave orbit.
Wait, wait a second. I'm going to send them fast. What shape, do you recognize what shape a conic section that is? It's not a parabola.
Exponential.
No, it's a hyperbola. You end up getting a asymptote right here and an asymptote right there. Yeah, it's a hyperbola. So all of the conic sections that tell you all the planetary motion. You get a parabola if you're on the surface of a planet, you throw something in the air. You get an ellipse or a circle when you're orbiting the planet, and you get a hyperbola when you pass it by. Yeah. I'm going to teach you one more thing, and that is how to send things into orbit and why astronauts on space stations feel weightless. Feel weightless. Here they come. Following is Isaac Newton's explanation for how you can send things into orbit. Back in his day, I don't think people thought you could do that. They thought, hey, you know, either you're an earthly object or a heavenly object, and that's all you can be. And Isaac Newton says, no, you can put something in orbit. And here's how he explained it. Let me just erase all this. Just a second here. So imagine you're standing on a mound, okay? And this mound is 5 meters high. Here's you standing on the mound. And you've got a ball in your hand, and you drop the ball, okay? How much time does it take to hit the floor or hit the ground? Well, hey, x equals 1/2 gt squared, you know, acceleration, 1/2 at squared, the v naught is 0. So my x is 5 meters. My acceleration of gravity is approximately 10 meters per second, 10 meters per second squared. You tell me how many seconds?
1 second.
Yeah, 1 second. And that's what we discovered on the balcony of the J building, right? When you guys were dropping things off the balcony of the J building balcony is approximately 5 meters above the floor, and you were getting approximately 1 second. Yeah. So this is 1 second. But let's say he doesn't drop it. He throws it horizontally at 5 meters per second. So now the thing is going to hit the ground. Tell me, how far from the base of this mound is that ball going to hit? How many meters? Remember, it's going 5 meters per second that way, and it takes a second to hit the ground.
5 meters.
5 meters, right? Because is it going to take 1 second to hit the ground? Sure, right? Because the horizontal motion doesn't affect its vertical progress. So this is going to be 5 meters. Okay? Well, I'm going to change that. He now has another ball, but he's going to throw that ball. Here, in just 1 second. This black one is 5 meters per second. He's now going to throw this ball 15 meters per second. So it's going to go a lot farther. Tell me, how many meters before it hits the ground?
15.
You guys getting 15 meters? Sure, of course. 15 meters. Okay? Here. He now has another ball. He's going to throw it a little bit faster. He's going to throw it 8,000 meters per second. You guys okay with that? So my question to you is this: how many meters away is it going to hit the ground?
8,000.
You guys okay with that? 8,000 meters. No big deal. Here, let me draw the picture. Okay.
I can't see this.
8,000 meters, yay. That was easy. Except for one thing. My drawing is now no longer accurate. What's wrong with my drawing? Yes, not to scale. I mean, I'd need to go a lot farther. But there's something else. Let's pretend it's to scale. Maybe I put that little jagged line there or whatever. But there's something else wrong with it besides the fact that it's not to scale. Yeah, Logan?
There's no curve in the Earth.
Thank you. The Earth is not an infinite plane. The Earth is a sphere. We're a ball, right? And by the time you get to 8,000 meters, sure, maybe 5 meters or 10 meters, it's pretty much straight. But 8,000 meters, you're going to start experiencing the curvature of the Earth. So let me make a more accurate drawing than this, okay? My drawing here, I'll use green. My Earth is actually curving. So my Earth is going to curve out from under. This is not the Earth. The green is the Earth. Well, you tell me, how many meters do you suppose the Earth curves when you go horizontally 8,000 meters?
5 meters.
5 meters. So tell me, this ball that I launched, is it any closer to Earth now than when it started? No, right? This ball has traveled 8,000 meters, it fell 5 meters, and it is still 5 meters above Earth's surface, right? It hasn't gotten any closer. So what happens if it goes another 8,000 meters and falls another 5 meters, but the Earth curves out from it another 5 meters? How far from the Earth is it? 5 meters. So what word describes this ball? Say again? It's an orbit. I just put the ball in orbit. All I need to do is throw it 8,000 meters per second horizontally, and it's in orbit. It's in orbit because as it free falls, the Earth curves out from under it, and it never gets any closer to the Earth. You guys see that? Now, I drew this so that it would be more obvious to you, but actually this 5 meters is right there. The 5 meters is a radial measurement. So it's just always, it's always going tangent to the Earth, and as it goes around the Earth, the distance between it and the Earth is always 5 meters. It never gets any closer. So this is a more accurate drawing, really, but I just wanted to make the point that it fell 5 meters, but the Earth curved 5 meters. Great. Why can't I do that right here? I mean, why not just from the roof of the J building launch something at 8,000 meters per second? Won't that be in orbit?
Trees.
Why not? What's working against me putting something in orbit if I just launch it from the roof of the J building?
Air resistance.
Yeah, air resistance, right? Air resistance. It might start off at 8,000 meters per second, but it won't be at 8,000 meters per second very long. Pretty soon it reaches its terminal velocity, which is probably like 100 miles an hour or something, and it's not going to go in orbit at all. So in order for me to send something in orbit, what am I going to have to do?
Terminal velocity would be 8,000.
What's that?
Get its terminal velocity to be 8,000.
Okay, that's true. So it's where am I going to have to be?
In a vacuum.
Yeah, in a vacuum. And there's no air resistance where I could get that sort of terminal velocity, so I'm going to have to be high above Earth's atmosphere. And so that's why all of our satellites are above Earth's atmosphere. You know, not because we're afraid it'll run into anyone. They're above Earth's atmosphere because we don't want them to be losing their velocity. They have to be in a situation where there's no air resistance. And so here comes my last question to you guys. Now that you know how things go into orbit, they have an incredibly high tangential velocity. Here, I'll even write it down in words. High tangential velocity. And however far it falls, Earth curves out from under it. That distance. In this case, every 8,000 meters it goes, it falls 5 meters, and the Earth curves out under it 5 meters. Here's my last question. Here's Earth. Here's the International Space Station. International Space Station. And you guys should know from your experience that the astronauts on the space station are weightless. They are weightless. They feel weightless. Tell me, why are astronauts on the International Space Station weightless?
There's no force acting.
What's that?
There's no force acting.
Thank you. There's no gravitational force on them. Well, look at this. In fact, remember, that space station is in close orbit. That space station is like where the spy satellites are. Is it because there's no gravitational force on them? No, there's tons of gravitational force on them. You see that? There's lots and lots of gravitational force. That's not the correct answer. Someone else tell me, why does he feel weightless? As these guys, say that again, who said that? Say again, Giancarlo? Yeah, he's in free fall, just like this ball here, right? They're in free fall. Astronauts are weightless, not because there's no force. If there's no gravitational force, they would go in a straight line and they wouldn't be in orbit anymore, right? They're weightless because they are in free fall. The same reason why, if you're in an elevator, okay, I want to remind you, your apparent weight, and I'm running out of time, your apparent weight is equal to what? What's your apparent weight always equal to? Thank you very much. Say that again, Fatima. Yeah, normal force. So if he's in an elevator, then the normal force is equal to his weight if the elevator isn't moving. But what if you cut the cable? What if he's accelerating downward now at 9.8 meters per second squared, right? Now his apparent weight is 0 because there's no normal force on him. When you're in free fall, your apparent weight is 0. Well, as Giancarlo said, you're in free fall. If I were to go to a poker table and ask the other 8 players, why are the International Space Station guys weightless? They would all say because there's no gravity, but they would all be wrong. It's because they're in free fall. Their apparent weight is 0 because they're in free fall. They're free falling around the Earth. Okay? Weightless because they are free falling. All right. Hey. Thanks a lot. Thanks for your patience. This was a long lesson. Thanks for sitting there all nice. See you guys.